Welcome to today's training about bacterial filtration capabilities of sterilization wrap. What we want to tell you first of all is that this training is a training for internal purposes. So this is not to be shared with customers. It can be shared with distributors. The objective of our training is to present you this new brochure, which is a very nice scientific piece that has been very recently developed. And you will see that there are different bacterial barrier filtration tests in there. We want to make sure that these are well understood and that the importance of this piece is well positioned. In the testing, we're going to go from larger particles, being a stock standard Staphylococcus aureus of 3 micron, we will be going to smaller particles of 0.3 micron, which is a salt particle. So these are not the usual tests that we talk about, hence this training. No, we have to talk about the different categories of bacterial barrier testing. A first category of bacterial barrier testing are the tests that you can find in EN ISO 11607. You see there the ASTM 1608 and the ASTM 2101. What these tests are going to do, one way or the other, you are going to test your material itself as a filter. So you will spit some bacteria on it and you're going to see how many come true, how many don't come true. These are what we call normalized tests. And by normalized, I mean they have one of these funny numbers from an official organization, and it's exactly described how these tests are done, how many bacteria they need for it, and it's also determined which labs are licensed to do this type of a test. So the first category is I am testing my filter. The second category is the whole packaging challenge tests. What are we doing there? You know the TNO test, you know the Dunkelberg test, which it's at the end of HE465. You know the ARA container study. The principle is always the same or similar. Whatever package you want to investigate, you're going to put that in an isolated room. You're going to use bacteria, a Micrococcus luteus, for instance. You're going to use very small latex particles. You're going to have a number of pressure changes, and then you're going to see if there's any ingress in that package. In other words, it's different from a BAV because what you're doing here, you're going to examine the probability that something gets contaminated after sterilization. And then the third category is what we are calling MPI. It is, does my package indeed stay sterile after 3 months, 6 months, 1 year? So that is typically you sterilize a number of packages, you start to open them up after 1 month, 3 months, 6 months, 1 year, and then you say in correct circumstances, this type of packaging can keep your instruments sterile for, I don't know, a year, 2 years. So these are 3 distinct different categories. Let's go to a couple of other basic principles. The principles of filtration mechanisms and log reduction. We know that our wrap functions as a very good filter, and that is due to mechanical filtration. What this actually means is bacteria is walking around basically on some sort of a particle. It's going to hit the fiber and it's not able to come through anymore. You have there impaction, interception, diffusion. That are the 3 ways that packaging material will, from a mechanical point of view, block the bacteria. There is also something called electrostatic attraction. Electrostatic attraction is exactly what we are doing with PowerGuard. And the interesting part of putting PowerGuard on the sterilization wrap is this drawing here, bottom left. You see that the mechanical protection or the mechanical filtration only starts to kick in properly at the moment that you have about a 1 micron particle. But what happens with the particles that are smaller? And then here at that junction, you have the famous 0.3 micron, which is in the literature also called the most penetrating particle size, meaning that it's about the nastiest thing that you can find to penetrate a packaging. Physically, mechanical filtration isn't doing anything on that. And this junction, that's exactly where electrostatic filtration is already active. Now, with Halyard's sterilization wrap, we have the combination of both, meaning that anything smaller than 0.3 and 0.3 will be picked up by our fibers due to the PowerGuard. And once the particles become bigger, we more rely on the mechanical filtration. Now, the other principle that we need to talk about is log reduction. Sometimes we see BFE values, and they're usually expressed in percentage, and we see a 99.9 or a 99.99. What does that really mean? Let's have a look at the surface here that we're going to contaminate with 1 million of bacteria. If we killed 99.9, there's 1,000 bacteria that remain. If we killed 99.99, there's 100 bacteria that remain. In other words, that additional 9 behind the comma is making a huge difference here when you're looking from a contamination perspective. Now, scientists, they don't talk in percentages. They talk in what we call log reduction. So your 99.9 is a 3 log reduction. Your 99.99 is a 4 log reduction. And you see that there's a tremendous difference in the number of remaining bacteria. So the 3 ways of counting filtration is percentage, which we know, beta ratio, which is not used here, and log reduction. Log reduction, when you go to Excel, you will notice that it's one of the formulas that sits standard in Excel. So you can calculate a log in Excel. It is an accepted method. Now, to illustrate log a little bit further, the previous slide showed that how much is still left. Here we are going to make it clear, what does log reduction mean? Going from a log 1 to a log 2, it's every time a step of 10. You see that every time there's 1 0 added. So a log reduction 6 is about 1 million that you reduced. A log reduction 1 is only a tenfold that you reduced. So we go here from 90% to 99.9999, which is a much bigger reduction. As an example, we have here a disinfectant. The first disinfectant only has a log 1 reduction. 10% of the bacteria will survive. Whereas once you come to a log 6, there's practically nothing left here. So log reduction is really counting the number of bacteria that are still present or that have been filtered out. biologists, bacteriologists, scientists, they are talking in LRV or log reduction values because it is more accurate as that is what you've seen in the two previous slides. Now, there's major organizations that all talk in log reduction, and your bacteriologists in the hospital and people in hospital hygiene will perfectly understand when you talk about log reduction. That takes us to the test results. We know now that there are different principles of filtration, the mechanical and the electrostatic filtration, and we also know that a log reduction is more efficient than a percentage. The tests that have been done across all different grades. So that means the tests were done in the US, that we went from an H200, sorry, to an H600, that it was a large sample size, meaning we took several lots from the competitive material in several thicknesses, and we took several lots from our own material in the various thicknesses. The testing has been done by a third party, by Nelson Laboratories. Nelson Laboratories is licensed to use the testing methods, and the testing methods that we used were all officially approved testing methods. We talked before about normalized tests. Well, to a large extent, we have been using normalized tests. We use the ASTM 1608 and the ASTM 2101. Both of those tests are used or recommended in the 11607. Look at the results now. The 2101 is a test that we have been using for years. You know, the famous 2500 Staphylococcus aureus. We know that the Staphylococcus aureus has a diameter of plus minus 3 micron. And as you can see from the picture, this is a test that has been developed for face masks. What are you going to do here? You're going to spray an amount of Staphylococcus aureus on top of that mask, and then you're going to count how many bacteria did not come through. We've always expressed that in percentage in the past. Now we have been counting it in log reduction. And you see here that the log reduction, we're well above 3 in these heavy grades. Yeah, is much, much higher than the log reduction obtained with a competitive material. That is barely, I would say, a 1.7. So if you really count the amount of bacteria that we filtered out, were the Halyard sterilization material in the heavy grades is 80% better than the competitive material. I told you in the beginning that we're going from bigger particles to smaller particles. With the ASTM 1608, we're going now to a smaller bacteria. It's the Bacillus atrophaeus. That's actually a spore, and it's only 1 micron. The situation is again the same. There's again an aerosol with the bacteria. The samples are in a little isolated room. They're clamped into that little room, and that room is, or that chamber is hooked up to a vacuum box. So we're going to spray these spores on the test sample, and at the same time we're going to create a vacuum. In other words, we're going to literally to suck the bacteria or the spore through the material. This means it's a much more challenging test because you literally suck the bacteria through, and the diameter of your bacteria is much smaller. And here, it's absolutely amazing what is happening here. We're again well above the 3 log, whereas competition doesn't even reach 1 log. So our material, the halyard material, is 350% more resistant to bacterial penetration because it's such a challenging test. And now we're going to come to the last test, and that is a salt test. This is not what we call a normalized test. There's no standard that describes this, but it is a generally accepted test for filtration. You can look this up on the internet and look for TSI sodium chloride aerosol, and you will find different little videos about how it works. What is happening here is we have an aerosol with salt particles that is going to spray that solution on top of the material that needs to be investigated. We are going to count how many salt particles that are coming through the packaging material, and that aerosol is going to spray at the rate of 85 liters per minute. Now, why are we using a salt particle here? Because this is quite easy to handle, and we are here at, let's call it the impossible point for mechanical filtration. It is a 0.3 micron particle size. So this is absolutely the ultimate test. If we would not have PowerGuard on our sterilization wrap, we would have similar results than any competitive material. And this is what makes us better. And you see here, this is, you can't count salt particles in a log reduction, but this is counted in percentages of efficiency. We are more than 70% efficient here for the heavy grades, whereas the competitive material is somewhere, I would say, close to 40. So we have a 90% better particle filtration. Be assured that this is a good scientific piece. Our wrap functions like a filter. It will allow the sterilizing agent to penetrate and keep the devices inside sterile. PowerGuard is exactly starting at that point of 0.3 micron, where mechanical filtration barely functions, and PowerGuard will make the difference and offers superior filtration. PowerGuard remains active throughout sterilization, storage, handling, and transportation. So that was it for today. I hope you enjoyed this recording.